Okay, so I want to go over the alpha particle distribution homework that I gave you. Um, so I have it entered in my calculator here, so let's just take a look at it. So this is a frequency distribution, and the first column here, this represents the number of particle emissions in 10-second intervals, and the second column represents the frequency of observing those particular emissions. So like we've observed 28 intervals where there were three emissions of alpha particles. Just to give you some context for what this data set represents. So I have over here, um, I've Googled a picture of a Geiger counter. And what a Geiger counter measures is the number of radioactive particles that fall on its sensor, so that bombard its sensor. And the data that we're looking at right now, it represents data that's been collected from a particular sample of an isotope of uranium. So this data set was created by holding like a lump of uranium in front of a Geiger counter. And I've got another thing here. So alpha particles, just remember, it's um, the nucleus of the atom radiates these alpha particles with some probability. So if you think about what's going on there, we have a lump of uranium, and that has a couple billion atoms, and each atom has a certain probability of emitting this alpha particle, of radiating away. If you look at these pictures here, an alpha particle is really just some neutrons and some protons. But each atom has a certain probability of emitting a alpha particle. So if you think about it, we have like a billion different samples coming from the same population, where each observation has a certain distribution. So each atom here has a certain probability distribution, a certain population distribution that determines the probability of emitting a particle. So what I'm trying to get at is when we look at this distribution, so that's what this distribution here is, the frequency distribution of these alpha particles. When we look at this in our stat plot, I got L2 entered in. So remember how we enter this in, since we have a frequency distribution, you're going to enter in L1, so that's the outcome list, and then the frequency list. So that's our L2. And if we graph this and then hit zoom stat, you see we get a normal distribution. And I mentioned this in class, but anytime you see a normal distribution in nature, like we see here, that suggests something is being averaged or something's being summed together, right? So the distribution of the alpha particle emissions is approximately normal, so that suggests there's some underlying phenomenon that's being averaged. And if you think about what's being averaged, it's because we have like a lump of uranium where each individual atom has the same probability of emitting an alpha particle at a certain period of time. So we have collected in this sample of data um, essentially the average emissions from this billion, like this pile of a billion atoms. So that's why we see a normal distribution here. Um, so with this classwork, I want to, I guess, review some of the things we've talked up to this point about, some of the functions we've introduced on our calculator, and how they relate to some of the functions we have introduced. So what I want to do is calculate the mean and the standard deviation of the alpha particle distribution. And in class, everybody was using the 1var stats program, and that's fine. But there is a way you can do this where you can store it. So what I'm going to do is I'm going to pass in L1 comma L2. So when we've been using the mean before, we just pass in one list. But because we have a frequency distribution, we have to pass in the outcomes and the frequencies of those outcomes. So the mean has an optional argument where you can pass in a frequency distribution. And we want to store that in, let's say, A. Whoops. Delete. Delete. Store. That doesn't want to cooperate. There it is. And then we're going to store it and say A. Alright, so there's the mean. And then we want to do the same thing with the standard deviation. So that is standard dev. And same idea, we can pass in a frequency distribution here by saying comma L2. And then we can store that in alpha B. And there's the standard deviation. So the idea with the second part of this classwork is we can model this sample distribution with its ideal population distribution using the shade norm function. So what we're going to do is hit distr. Actually, we're missing a step. Sorry. So this frequency distribution is, these are the actual frequencies. In order for this to work right, we have to calculate the relative frequencies. So we have to take this list and divide it by the total number of samples. So we need one more piece of information. And that's a list operation, actually. So the dim, that gives you the length of a list. However, we have a frequency distribution, so we don't want to calculate a length of a list. You think about what we have here. This column is telling you how many observations occur for each outcome. So what we need to calculate is the sum of this column. That will tell us how many total observations we have. So we're going to go over to second list, and that is under math. So we want to calculate sum L2. And let's go ahead and store that in, let's say, C. Okay, so step we missed. Let's go ahead and do it. We want to calculate the relative frequency distribution. So that's going to be L2 divided by the total number which we stored in C. Alright, so let's change our stat plot real quick. So just to recall, this shouldn't actually change the shape, but it's going to change the scale. It's one of our data transformation theorems. Whoops. Zoom. I must have entered something wrong. What do we think about that? Frequency. Let me make sure everything worked out. That looks good. Second stat plot. Alright, so frequency distribution is on. X list is L1. Alright, let's graph. Why is it giving me that weird? It might just be... Why is it setting that scale? Okay, so just be careful with the scale. For some reason when you hit zoom stat, it's not doing it quite right. Still not a good window. Let us... There's a way we can get this. We can take the max... Well, hold on. Let's make sure it's clear. We can take the max of the relative frequencies to figure out what the maximum y should be. Alright, there we go. So let's hit graph again. Alright, and then we should probably shorten the X window to give it, so we can see the whole thing. So that should be the max of the outcomes. So we're going to go over to the max, and the outcomes are stored in L1. Okay, so let's try that again. Okay, there we go. Nice and normal. It's important that we graph the relative frequency because we're about to fit a ideal distribution to this. So we have the right window, we have the right frequencies. I think we're ready to go. So the idea here is this curve is approximately normal, and we have a ton of samples with this data set, 1200 about. So this should be pretty close to an actual normal distribution. If we go to second distr, there's this shade norm function that we introduced. So what we want to do is shade in the ideal normal distribution that represents this sample distribution. So we're going to take the minimum observation, which we can calculate it directly in here. We can say list max L1, right? Because that's our outcomes. Sorry, that should be min. Let's do that again. Min L1, and then max L2. All right, and then the mean, remember we stored that in A, and the standard deviation we stored that in B. All right, so if we draw this, that didn't work out to be correct. Let's try that again. I might have had something typed in. Max L1. There we go. Right, it should be 0 to 19. So the minimum observation and the maximum observation. And if we draw this, take a look at that. It's pretty good, right? It almost fits it perfectly. So this is a example of actually two different things at once. It's the law of large numbers, because we have a very large sample, so we get a very, very smooth histogram. It's approaching its true population distribution. And we also have a little bit of the central limit theorem going on. However, that's kind of going on in the background. It's the averaging effect of the alpha particles, because you're holding up a sample of like a billion atoms, and each one has the same probability of emitting a alpha particle. The other thing to note here is the percent of the distribution that is between the min and the max. So if you take a look there, it's going from a low of 0 up to a high of 19. That's the min and max of the observations that we've seen. But that doesn't constitute 100% of the ideal normal distribution. So there's a few reasons for that. The one everybody gets when I ask this is that the normal distribution asymptotically approaches 0, so it never actually gets to the 100%. The other reason that I want you to think about is this is still a sample distribution, right? 19 might not be the true max. There's always a chance that we drew a sample where we didn't get every single possible outcome in our sample. That's an important idea in statistics, that there's always this element of chance anytime you draw a sample. Now, the other part of this is looking at the CDF. So, in order to do that, we need to approximate the CDF. So the CDF, remember, is just the cumulative frequencies. So we're going to create a new column here, and we're going to add up all of the frequencies in L3. So that, remember, is one of the list functions here, the cumulative sum, and you just pass in L3. All right. Now, remember how we graph these. This is not a like bar chart histogram. It's a line graph. So that's this one. And then the marker doesn't necessarily matter. If we graph, for this one you do have to hit zoom stat, I think. Alright, so this is our CDF. Remember, this is the function that always approaches 0 as you move to the right, and it approaches, I'm sorry, I said that wrong. It approaches 1 as you move to the right. So that's the, you can see my taps right there, right? It's going up to the 1. In other words, behind the maximum observation, you get 100% of the distribution. So remember, you can hit trace and go through these. So the y value here, that's the percentile, right? So this, for instance, would be saying 17% of the distribution is less than or equal to 5. This would be saying 27% roughly is less than or equal to 6. So the second part of this is going to ask you to estimate the 90th percentile. And remember how you do this. You look for where it skips over 90. So we're at 85%, that's the 11 emissions. All right, so between 11 and 12, it goes above 90%. So that means the 90th percentile is roughly 12 emissions. Now, that is the sample percentile. That's how you get the sample percentiles using the CDF. We also introduced this new function called the inverse norm, which remember is just the inverse of the CDF. right? You input a percentile and it tells you the corresponding observation from that distribution. So if we ask for the theoretical 90th percentile and we insert our mean and our standard deviation, ooh, I hope that works. Yeah, okay, it works. Usually it changes the A and the B to their actual values. But anyway, notice that this is very, very close to what we observed, right? It's 12.13. That's almost exactly 12. So this is how we can model our sample distribution using these density curves that we've introduced. So this will be kind of like the basis of statistical inference, is how we can use these functions to model population distributions. So that's why I made this video, because this is kind of an important idea. I want everybody to be on the same page about this. So just refer back to this video when you have questions or concerns. Now, how do I quit this?